This is IAT355 Visual Analytics Lecture 9, where we're going to be talking about trees. So this lecture is going to take place in a number of parts. And of course, we're all familiar with botanical trees. We use them every day. And we're also familiar with trees in, say, a file system. But today what we're going to be talking about is all sorts of different types of trees, which have three broad approaches to doing layout of the information. So the first thing we'll talk about today is NodeLink diagrams, in which there's an explicit representation of the relationship between one node and another in a tree. So let's get started. So what we're interested in talking about today is hierarchies. And a hierarchy is a data repository in which cases are related to subcases and sub-subcases. An example that we're all familiar with is, say, the organization chart of a corporation or something like that. You might have the president at the top, the vice presidents, the managers, maybe some branch managers or something like that, and various categories of employees. And we'll show an example later on where we talk about visualizing a structure just like that. In any case, we can be, when we're doing visualizations on information like this, we can think of imposing an order on which cases are parents or ancestors on other cases. Some of the time, that order is just natural. It kind of is an outgrowth of exactly how we think about the management structure of an organization, or grandparents, parents, children, etc. But in other cases, the part of the analytical job is to create that order. And so that's both of those situations are what we're going to be talking about today. So examples, well, as I mentioned earlier, family trees are an example of that. You have one pair of grandparents, parents, children, grandchildren, etc., etc. You could also trace upwards. That is to say, you have your two parents as your immediate ancestors, your four grandparents as their ancestors, and your great-grandparents, 8 of them, all going all the way back to who knows how far. Another example that we use every day is file and directory systems on computers, organization charts, as I said before, as well as taxonomies. And this is a very common use for tree diagrams. And that is taxonomy or organizational structure in which you have a large category, subcategories, sub-subcategories. The detailed categories have more detail, have more information, and typically in a taxonomy system, the organizational idea is that the information at the top is general, and as you go down the taxonomy tree, the information gets more and more and more specific. So at the top you have animals, and then within that you have, say, mammals versus reptiles, and then within mammals you have, cows, people, monkeys, that kind of thing. So, of course, that is a very coarsely detailed tree of life that I'm quoting there. So, tree hierarchies like that are often represented as trees visually. And a tree, formally, is a kind of graph, and that is to say a node-link structure in which there are no cycles. And what that means is that if you go from node to link along a link to another node, along another link to another node, you can't go trace a path so that you can get back to the starting place. There's only one way to go from here to there in a tree, and that's how trees are defined formally. So there are 3 main visualization styles for representing trees. One is the node-link diagram. The other is space filling, or enclosure, as Munster says in her book. And the third is matrix, and we'll deal with that third. Okay. So when we're thinking about drawing trees, one of the things that we want to be able to do is to learn a number of things about the tree. One of the most important things typically that we want to be able to do is to learn the structure of a hierarchy. So an example structure questions are things like, who has the most descendants? Let's say you start with people born in 1900 and you're comparing individuals and you'd like to know which of those 10 individuals that you're looking at has the most great-grandchildren, children, grandchildren, great-grandchildren, and so on. You might also ask what family, what group of genetically related individuals have the most children overall, for whatever reason. An example search question on that thing, where those previous questions were structure questions, is, who is somebody's paternal grandfather? Who's the father of his father? Things like that. So in both of those things, you can imagine that showing a picture of the tree that looks like a tree can be really instructive and informative at telling you what the relationship looks like. And to answer these kind of numerical questions in the middle, and these kind of search questions like this, similar to who is Bob's grandfather. So to start with, simple tree diagrams typically look something like this. Over on the right, we see a collection of nodes and linked by typically straight lines, but not always, and they're linked to other nodes. Typically, there is a single link from one node to another. There's at its simplest, there aren't multiple links. There are situations in which multiple links make sense, the other thing that is the case is that there is a well-defined root that is typically drawn at the top, and the descendants or child nodes are placed below or downwards in visualizations like this. So on the right, we have a tree with 6 nodes in it. The root is here, and then 2 child nodes and 2 grandchild nodes. Here's another one. In this case, we're not explicitly drawing the nodes. They're implied in, the bends in the line. So there's a node here at the root. There's 3 children, and there's 1, 2, 3, 4, 5, 6, 7 grandchildren, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9 great-grandchildren. Now, confusingly, perhaps to mix metaphors, the name of these things takes on botanical names. So the root is at the top. I know, the tree's upside down. And leaves are at the very bottom. And in fact, leaves are nodes that do not have any child nodes. So we're mixing, person and, botany together here in terms of the terminology for trees. But in any case, leaves are at the bottom. Leaves don't have children. A root does not have any parent nodes of any kind. So it is typically also the starting place. And in a file system, you're used to that by virtue of that's where, the C drive is, or something like that. So a sample representation is now what we're showing. This is from Johnson and Schneiderman's paper in 1991. And here, what we're doing is we're allocating space in a kind of an orderly manner. Each row, each generation, each layer from the root gets its own piece of horizontal space, its own swatch going across. And the marks that indicate the links from root to child node are drawn in the space between where the root's nodes are and the root's child nodes are. And so, there's this alternating allocation of horizontal space for nodes, the link marks, nodes, link marks, etc. So A is the node, B, C, and D are children, F, G, H, I, J, and K are grandchildren, L, M through to T are great-grandchildren, and great-great-grandchildren are UVW. The other thing that's being shown here is also a weight or a number, and that quantitative value is being added up towards the root here. So as you can see, this tree is not terribly dense or terribly bushy, so it can fit easily on a page, and you could understand its structure fairly simply. We could also put these names on things, saying what kind of information. These are grandchild nodes here, great-grandchild nodes. These are grandchild parent nodes. Grandparent nodes, however you want to term it. So in any case, that's an example of a layout. Another layout, which is something that we see all the time, certainly in Windows, we see layouts that look exactly like this, because this is of course stolen from my file system probably a few years ago now, and this is just an element of the C drive on my computer, and I have a copy of Adobe After Effects on this machine. In any case, the way in which the layout works is the tree level is indicated by the distance from the left boundary. So this is up above, there's an indicator of the C drive. It's just not shown here in this image. And this is the immediate child nodes of the C drive. The suite of folders directly within the first layer of C. And then within that, we see program files is open, and there we see the Adobe folder is open and its child nodes, the Apollo folder, the Apple software folder, ATI Technologies, etc., etc. So this is an older screenshot of the Windows file system in which we're showing the individual folders. The tree level is indicated by the distance in X from the left boundary. And of course, the other allocation idea is that there's a unique piece of real estate, a vertical real estate, a horizontal slice for each individual folder. On the right, there's a companion view, of course, which we all use, and that is either, it has multiple visualization styles. You can show icons, you can show a detailed list that looks like this. And depending on what you want, you might see the pictures, you might see the icons, you might just see file names. The whole concept is that, of course, interacting with this view here causes changes in the primary view to show the contents of the folder that you've selected. And this concept, of course, takes advantage of reading order. The order in which you read things from top to bottom is the concept that's going on in here. It's built for a particular suite of tasks. And I say here, what it's good for is search, particularly if you're doing visual search. If you know the structure well, then you kind of know what the names are in the file system to look for and how to navigate from place to place. And that works well with the internet technology that we all use. We use free text search, and if you're looking about where to find a control panel or where to locate a particular folder or something like that, hopefully you have remembered a bunch of names for where things live. You have the courses folder within your home directory, and in that is where you find the stuff that's, say, about IAT355. Now, so one of the things it's good for and what it's built for, because the usual activity is to search for a folder, to open it, and then start working on the files in it, it's good for search to enable that task to happen reasonably well without too much heartache. What it's not so good for is to understand structure. So if you wanted to understand the structure of this entire file system, opening up all the folders isn't going to help you, because what happens is that the length of this thing gets to be, I'm running out of camera range. It gets to be very, very, very long. Perhaps meters upon meters long if you were to open every folder. But of course, the reason why we still use it is instead of, say, some third-party file viewing software, is because we're not usually using this system to understand its structure. We're usually using the system for search. And so it's not good at structure because it's not built for it. And the reason why, among the reasons why it's not good for understanding structure, is that one folder per row pushes large structures further down. And if you open something like program files, you get a huge number of folders to appear that push all the stuff that's below them out of the way. And some of the time, one of the ways in which you use this is to kind of remember, where was I in the file system, so that you can remember tasks and so on. And that's how I use it. In fact, sometimes this isn't an example of that. This is just to demonstrate the technique with a program files folder open. But for my own home directory, I have a bunch of stuff open, and it's open because I want to be able to get at it. There are other techniques that have been brought to bear to make that easier. The recently used list and things like that. Okay, so that technique is to enable search and to locate deep in the hierarchy some particular thing and then start working on it. To show structure, some other techniques have been developed over the years. And so this one is intended to show structure And what it does is, once again, allocate horizontal space, a level of the tree, level from the root, the number of steps from the root node, which is once again at the top. Each level gets its own chunk of space, and the horizontal space is computed according to the accumulated number of nodes that are present down below. And so what drives this layout here is an algorithm which searches throughout the tree and measures the number of descendants from top to bottom and allocates space according to the most number of descendants. And you can see that's going on here, that a lot of space has been allocated horizontally to this chunk because there's, I don't know how many, 30 or 40 nodes here. Only one of those nodes has any children, but we need to allocate a lot of space so we can allocate so that the minimum possible amount of space per node can be allocated for each one of those 30-odd items. And the same is true of this one here. All this has one child and 3 grandchildren. So basically, space is measured, it's accumulated, and space is laid out according to the amount of space that is needed from top to bottom. So the way in which that's done is through an algorithm called depth-first search. There are two broad categories of searching algorithm. Depth-first, the way it works is you start at the node, go to the first child, and then from that child to its first child until you reach a leaf, and then go up and then go to the next, great grandchild, the next one, and go up and accumulate information and do that throughout the tree. The reason for doing it that way is it doesn't take up much memory. Anyway, the idea with this thing is you propagate size requirements up, and that tells you how much space is needed. And then the layout algorithm allocates space according to the amount of space that has been measured in the first pass of depth-first search. So one of the problems with algorithms like this is that for top-down, the width of top-down layouts like this, the width of fan-out, that is to say, just simply the number of things coming out from an individual node or the accumulation of nodes, uses up screen real estate very quickly, and we'll show examples that address that a little later on in this lecture. So let's say, for example, that at each step from the root, there are 2 times the number of nodes than there were at the previous level. That is to say, each child has 2 children, and each grandchild itself has 2 children, and each great-grandchild has 2 children. So you would end up with 1, 2, 4, 8, 16, etc. nodes. If you had a depth of 10, that means you have 2 to the power n nodes, and that 2 to the power 10 is 1,000. And if you had 20, 2 to the power 20 is roughly 1,000,000. So you end up, if you have a big enough fan out, even if the fan out factor is 2, you end up with trees that take up a lot of space. These examples we've shown here so far aren't that big. The tree that I showed first of the file system is that big. There is an enormous number of files in your typical Windows installation, and that's another reason why. You show nothing to start with. You show just basically that there is a C drive, and then you rely on the user interaction to activate it and do some things with. So because a tree might grow a lot along one particular branch, either an algorithm can be run to figure out what the fan out is below, or you just accept that when you're doing layout, you're just going to have to accept that some things are going to be hard to see or some other compromise needs to take place. So in essence, it's no matter what the concern is, no matter what the fan out is, rather, it's hard to draw it well in the view without knowing how it will branch. So InfoVis Solutions are basically techniques that have been developed in the field of information visualization to try to assist with problems identified of fan out not being predictable like O is 2 times n, but being variable and having a large range. Sometimes you might have 500 files with 500 folders, and other times you might have 2 per folder. And also, information viz techniques attempt to show more attributes of data cases in the hierarchy or focus on particular applications of trees. The things we've shown so far are really saying all trees are created equal and all we want to do is know structure. As visualizations to show structure, they were okay. but they had the drawback of you didn't know in that previous diagram what any of those nodes were about. They're just dots. So this thing here is called SpaceTree, and what this thing does is it uses kind of conventional 2D layout techniques, but it uses interaction as a means of managing space. And this was done by Grosjean, Plaisant, and Peterson at InfoVis in 2002. And what we're going to do now is show a video of that. Please hold. Okay, so here we go. So this is SpaceTree. And to start with, what we're doing, the demo is doing, is opening individual nodes. And when a node is clicked on, space is created and the node expands. This thing also supports search, which you can see. So we're just doing SCI. That's showing up those things in red. What I'm going to do is I'm going to play it again. And what the search does is show all the scientists. You'll notice something interesting that happens with this, and that is it moves the tree around in order to make space. So right now, I just paused it. The demoer has typed in SCI for science, and it has highlighted all the places where scientists are, or scientists occur in the org chart. And what it will do is show these red triangles. And what the red triangles indicate is that those are descendant nodes. The horizontal extent of the triangle indicates how deep they go, and the vertical size indicates how much stuff is and how many descendants there are overall. The smaller the little triangle, the less descendants there are, the fewer the descendants there are. One of the things that's also very important about this thing is it allocates space first before putting stuff into that space. And the reason for that is to enable you to concentrate on what's going on. So let's press play again to continue that. They've just entered SCI, and then you can see that the science query has been expanded there. And I'm paused it once again, and you can see that these things are all the forest scientists who, work in the Acme Tree Movers Vice President's office. Let's play that one more time, and then I'll pause it one more as we go along. One more time. And so we clicked on exploration, and you can see here in the starting view, there are just a few nodes present there. There's lots here, here, and here where the scientists ended up being. So exploration was clicked. The 6 or so employees showed up, and now clicking on support function, it first hides the old stuff. We can see it's caught in the middle of hiding, shrinks it down, and then expands into that space the stuff that was the descendant of support functions. And now, as it continues on, we click on IT Manager. This tree moves to the left to create space for the details to show up to the right, and it shows 2 levels of the hierarchy. And now exploration is clicked once again. The space is reallocated because it would dismiss the old stuff, dismisses it, moves the tree so that it's more fully visible, shows the new stuff. And then once again, we're going to do search in order to show what's going on. Those are all the scientists. Okay, so that video goes super fast. That's why I played it a bunch of times. But the basic concept is that what we're wanting to do is to lay things out and allocate space as you need it, and deallocate space that you don't need. There's a vertical versus a horizontal version. We'd shown the horizontal layout in the video. And as I said verbally, and you could see in the video, subtrees are triangles. The size of those triangles indicates the depth. The shading indicates the number of nodes inside. The darker the shading, the more nodes. And you navigate by clicking on nodes. And it also strongly restricts zooming. We talked about zooming the other day for geometric zoom. This is kind of a semantic zoom a little bit. There's something fundamentally geometric about it, but details show up that would overlap other details. So it's not strictly geometric because there's not some existing layout in which you're just moving the camera closer or farther away from. You're doing a different kind of zooming here in which the details are showing up, and space is being used for some descendants, and then unused for that descendants to create space for a new set of descendants to be shown. So an interesting concept with respect to zooming there. So one of the things that you've no doubt noticed is that you can read all those labels once the stuff stopped moving around. And this also enables the layout algorithm to maximize the number of levels opened. It also carefully, as I pointed out in the last repeat, decomposes tree animation, dismisses the old stuff, moves the tree around such that it will be at a root that has enough space to put its descendants into, and then expand its descendants from nothing into that newly allocated space. And part of the reason for that is it's trying to not overload your perceptual capabilities. Presumably, when you're clicking on a target, you're looking at that target and you have a sense of what the overall shape of the tree is. When you click on it, it moves that stuff rigidly either to the left to make space or to the right to reclaim space. When it's doing that, what it does is it keeps the stuff that is, the parent and grandparent, all the way up to the root, keeps that stuff stable so that it doesn't move it around, so you can maintain a clear understanding of where you are in the hierarchy. So if you're thinking of the hierarchy as a structure that you want to learn about, maintaining a clear picture of that hierarchy can be very important. And at least in this visualization, that's something that they wanted to. So that concludes part 1 of NodeLink diagrams. What we will do now is move on to part 2, where we talk about different approaches to doing NodeLink diagrams that use more advanced geometry, among other things.